Welcome back to the deep dive. Today, we're plunging into, well, one of organic chemistry's really fundamental challenges.
Yeah,
Imagine you've got a molecule, right? And it has loads of different reactive buttons, these functional groups. How do you push just the one you want?
exactly. Without accidentally setting off all the others. It's like molecular surgery.
Yeah, molecular surgery, I like
And the answer really is selectivity. It's all about controlling which part of a molecule reacts and how. We generally break it down into three main types. There's chemoselectivity, that's which functional group reacts.
Okay.
Then regioselectivity, that's where on the molecule it happens.
Right.
And finally, stereoselectivity, which deals with the how, the 3D arrangement of the atoms in the product.
Got it. And for this deep dive, we're really zeroing in on chemoselectivity, yeah?
Yeah.
The art of making sure only the functional group you want to change actually, well, changes.
Precisely. And we're drawing heavily from Chapter 23 of that fantastic textbook, Organic Chemistry, the second edition by Clayden, Greeves, and Warren.
It's a classic. Our mission today is to unpack the why behind it, the mechanistic reasoning, look at key reactions, functional group transformations, and sort of see how this all builds towards bigger ideas like retrosynthesis. We want to make it super clear for you, especially if you're an upper-level undergraduate listener.
Absolutely. Let's lay that foundation.
Okay, so you mentioned the three types. Can we just quickly define them again, maybe a bit more formally, just to be crystal clear?
Sure. So chemoselectivity, our main focus today, asks which functional group reacts. If you've got, say, an alcohol and an aldehyde, how do you hit just the aldehyde? That's chemoselectivity.
Yep.
Regioselectivity is about where. We've actually touched on this before, maybe without using the label explicitly. Think electrophilic aromatic substitution. Does the new group go ortho, meta, or para? Or, 1,2 versus 1,4 addition to unsaturated ketones. That's regioselectivity.
Right, position matters.
Exactly. And then stereoselectivity is about the 3D outcome. Are you getting a cis product or a trans product? Things like that. We'll definitely get into regio and stereoselectivity in more detail later on. But yeah, today is all about the which one chemoselectivity.
Perfect. That distinction is really helpful. So let's make this concrete. A really common example you often see is making paracetamol, right? Starting with 4-aminophenol and acetic anhydride.
Oh yeah, that's a textbook case, literally. So 4-aminophenol has two potential reaction sites for acylation. The amine group, NH2, and the hydroxyl group, OH. Both can react with acetic anhydride.
But they don't react equally well.
Not at all. The amine nitrogen is way more nucleophilic. It's much keener to attack the acetic anhydride than the oxygen of the hydroxyl group is. So the trick is, if you use just one equivalent of acetic anhydride and maybe a mild base like pyridine, you can get it to react almost exclusively with the more reactive amine group.
Giving you paracetamol.
Precisely. That's chemoselective acylation in action. It relies purely on the inherent difference in reactivity between the NH2 and OH groups.
That's a brilliant illustration.
Right.
And it points to a broader principle, doesn't it? This idea that some functional groups are just naturally more reactive towards certain reagents, like nucleophiles.
It really does, especially with carbonyl compounds. There's a fairly predictable hierarchy. Generally speaking, aldehydes are the most reactive towards nucleophiles.
Okay.
Then come ketones. Then esters are less reactive still, followed by amamides. And finally, carboxylate anions are pretty unreactive.
And that order comes down to?
It's a mix of things. Sterics play a role. Aldehydes have a hydrogen, so they're less crowded than ketones. But electronics are huge too. In esters and amides, the lone pairs on the adjacent oxygen or nitrogen can donate electron density into the carbonyl group through resonance.
Right, which makes the carbonyl carbon less positive, less electrophilic.
Exactly. Less attractive to nucleophiles. So understanding this basic reactivity ladder, aldehyde, ketone, ester, amide, carboxylate, is, well, it's fundamental for predicting chemoselectivity.
Okay, so we can exploit these natural differences. Now, let's dive into an area where this is absolutely critical, reduction reactions. We're not just, blasting things with hydrogen. We need precision.
Oh, definitely. Reductions are a fantastic playground for chemoselectivity. Take the synthesis of salmefarmol, that anti-asthma drug developed by Glaxo. That synthesis is a masterclass in using different reducing agents for specific jobs.
How so?
Well, at one stage, they might use sodium borohydride, NaBH4. It's relatively mild, right? So it can reduce a ketone functional group but leave an ester group completely alone in the same molecule.
Okay, selective for the ketone.
Then later, they might need to reduce that ester. So they bring out the big guns, lithium aluminum hydride, LiAlH4, which is powerful enough to reduce the ester.
Got it. Different tools for different tasks.
Exactly. And maybe in another step, they use catalytic hydrogenation, that's H2 gas, with a palladium catalyst to selectively reduce, say, a carbon-nitrogen double bond without touching other things. Each region is chosen for its specific chemoselectivity.
That really highlights the importance of the region choice. Let's dig into those carbonyl reductions a bit more. Why NABH4 for aldehydes and ketones? Why not just always use the more powerful Lyell H4?
Good question. NABH4 is much gentler. It works nicely in common product solvents like methanol or ethanol. It delivers a hydride equivalent, basically, H to the carbonyl carbon.
Okay.
The main advantage is handling and safety. NABH4 is relatively stable. You can even use it in water sometimes. Lyell H4, on the other hand, is ferociously reactive. It reacts violently with water, can even catch fire. So while Lyell H4 would reduce aldehydes and ketones, it's often overkill, less selective if other groups are present, and just plain more dangerous to handle. NABH4 is usually the safer, easier, and often selective enough choice for those groups.
Right. Practicality matters.
Okay.
What about reducing esters or amides? You said Lyell H4 is the choice there.
Typically, yes. Lyell H4 is strong enough to take esters all the way down to primary alcohols. For amides, it takes them to amines. Interestingly, the mechanism for amide reduction is a bit different. It goes through an intermediate called an aminium ion before the final reduction to the amine.
I see. Any alternatives for those?
Well, for amides, another good option is borane BH3. It's also quite effective at reducing amides to amines, sometimes offering different selectivity. And for esters, if you need something a bit milder than Lyell H4, lithium borohydride, LiBH4 can sometimes do the trick, maybe reducing an ester in the presence of an acid or an imide. NABH4 is generally too slow with esters to be useful.
Okay, borane BH3. That one's interesting because it also reduces carboxylic acids, right, which Lyell H4 does too, but borane is often preferred. Why is that?
Yeah, borane is great for carboxylic acids. It's usually used as a complex, like BH3.THF. Now, unlike the borohydrides, which are hydrodonors, not the nucleophiles, borane is a neutral molecule with an empty p orbital. It's a Lewis acid.
So it behaves differently.
Completely. It prefers to react with electron-rich carbonyls. Carboxylic acids and amides fit that bill. It coordinates to the carbonyl oxygen, activates it, and forms this intermediate, triacyloxyborane, which then gets reduced. Because it's a Lewis acid interacting with electron density, it's often highly chemoselective for carboxylic acids and amides, leaving potentially more electrophilic groups like esters or ketones untouched. It's a really nice example of exploiting different electronic properties.
That's clever. Okay, here's a common headache, I imagine. Reducing an ester or an amide, but stopping at the aldehyde stage. That seems tough because aldehydes are usually more reactive than esters, right? So wouldn't it just keep reducing to the alcohol?
You've nailed a classic problem in synthesis. Yes, aldehydes are typically more reactive towards hydrides than esters or amides are, so simple reduction usually blows right past the aldehyde to the alcohol or amine.
So how do you stop it?
There are a couple of key strategies. One, which is sometimes necessary, is indirect. Reduce the ester all the way to the alcohol, and then carefully oxidize it back up to the aldehyde using one of the selective methods we'll talk about later.
Okay, 2 steps. Any direct methods?
Yes, thankfully. The star player here is often dibyl, or dibyl H. That's diisobutyl aluminum hydride. It's an aluminum hydride and a lane, also a Lewis acid type reagent. The magic of dibyl is that when you use it at very low temperatures, like -70 or -78 degrees Celsius, it adds to the ester or nitrile, but it forms a relatively stable tetrahedral intermediate.
It gets stuck temporarily.
Exactly, it just sits there at low temperature. Then, when you add water during the workup to quench the reaction, that intermediate collapses and you get your aldehyde. Because the aldehyde is only formed during the quench, it doesn't have a chance to react further with any remaining dibyl. It's very neat.
That's really elegant. Works for other things too.
Yeah, it's great for reducing lactones cyclic esters to lactols, which are cyclic hemiacetyls, and it's also the standard way to reduce nitriles to aldehydes. For amides, sometimes you can stop at the aldehyde using Lyell H4 carefully at low temperature, like 0 degrees C, where the intermediate is a bit more stable.
Okay, so we've got this amazing toolkit of hydride reagents, NABH4, Lyell H4, borane, dibyl, each with its own personality and specific job. Now, let's switch tracks to hydrogen gas, H2, as a reducing agent. Catalytic hydrogenation. You said this isn't usually for carbonyls.
Generally, no. H2 itself isn't nucleophilic enough to attack a typical carbonyl group, but it's fantastic for reducing other types of double and triple bonds, or carbon double bonds, alkanes, carbon-carbon triple bonds, alkenes, carbon-nitrogen double bonds, evalvins, nitro groups.
How does it work?
You need a catalyst, usually a finely divided transition metal like palladium on carbon PDC, platinum PT, or nickel Li. The basic idea is that both the hydrogen gas and the molecule you want to reduce adsorb onto the surface of the metal catalyst. The HH bond breaks, and the hydrogen atoms are then added across the double or triple bond of the organic molecule also on the surface.
And it usually adds hydrogens from the same side.
Yes, that's a key feature. It's typically a syn addition, meaning both hydrogens add to the same face of the double or triple bond.
Right.
If you reduce a cyclic alkene, for example, you'll get a cis-substituted cycloalkene.
Okay. And does this show chemoselectivity too?
Oh, absolutely.
Yeah.
For example, take a T-unsaturated ketone one with a CC double bond next to the CO group. Catalytic hydrogenation will almost always reduce the CC bonds selectively, leaving the CO untouched.
Interesting. That's the opposite of what some hydride reagents might do.
Exactly. It contrasts nicely with something like the Lucia reduction using NeBH4 with cerium chloride, which selectively reduces the CO in those systems, avoiding the CHC. So you have choices depending on what you want to achieve.
What about alkenes? Can you stop at the alkene?
Yes, and that's a crucial application. If you want to go from an alkene to a cis-alkene, you use a special catalyst called Lindlar's catalyst. It's basically palladium on calcium carbonate that's been poisoned with lead acetate and quinoline.
Poisoned.
Yeah, the poison deactivates the catalyst just enough so that it reduces the alkene to the alkene, but then it stops. It prevents the further reduction of the alkene all the way down to the alkene. It's a very delicate and important chemoselective reduction.
So Lindlar gives cis alkenes. What if you want trans?
For that you typically use a dissolving metal reduction like sodium in liquid ammonia, which we'll get to. They're complementary methods.
Okay, hydrogenation isn't just for CEC and CC though, right?
No, definitely not. It's key in reductive amination, where you form an imine and then immediately reduce it with H2 catalyst to get an amine. It's also a standard way to reduce nitro groups, NO2, to amines, NH2, often much cleaner than older methods like tin and HCl.
And you also mentioned hydrogenolysis earlier, breaking single bonds.
Yes, hydrogenolysis is really important, especially for removing protecting groups. It uses H2 and a catalyst, typically palladium, to cleave certain types of single bonds, most commonly carbon heteroatom bonds next to a benzene ring, what we call benzylic positions. So benzylic ethers, CO bonds, or benzylic amines, CN bonds, can be cleaved. In that salmophamal synthesis, benzyl groups used to protect alcohols were removed this way.
Does the catalyst matter there?
It can. Palladium is usually best for cleaving benzylic CO bonds, while platinum or rhodium might be better if you also want to reduce the aromatic ring itself. So again, selectivity through catalyst choice.
Okay, so hydrogenation is versatile. Now, thinking about simplification.
Right.
Sometimes you just want to completely remove a functional group, right?
Yeah.
Especially carbonyls. How do you get rid of the CO and replace it with a CH2?
Yeah, sometimes you just need to deoxygenate. For carbonyls, there are a few classic powerful methods. One is the Wolff-Kishner reduction. You first convert the ketone or aldehyde into a hydrazone derivative, and then you heat that with strong base, like potassium hydroxide, in a high boiling solvent. Nitrogen gas bubbles off, and you're left with the CH2 group.
Okay, we require strong base. Any alternative?
Yes, the Clemmensen reduction. This uses zinc metal that's been amalgamated with mercury in concentrated hydrochloric acid. It's a type of dissolving metal reduction using the electrons from the zinc metal under very acidic conditions to achieve the same transformation, CO to CH2.
Acidic versus basic conditions. Useful to have both.
Definitely. Which one you choose depends on what other functional groups are in your molecule and whether they can survive strong acid or strong base. For example, in one synthesis of muscalor, the housefly pheromone, they used the Wolff-Kishner to get rid of a ketone. Another synthesis of the same molecule used Lindlar's catalyst to make the Z-alkene, showing how these methods get combined.
You mentioned dissolving metal reduction with Clemmensen. Can we explore those a bit more? What's the core idea?
It's pretty cool, actually. You take a very reactive metal, like sodium or lithium, and dissolve it in liquid ammonia, usually at low temperature, like Nanix 33 degrees, or even Nanix 78 degrees C. These metals readily give up their outer electron. In liquid ammonia, these electrons become solvated, surrounded by ammonia molecules, creating this intense, deep blue solution.
Solvated electrons.
Exactly. And these solvated electrons are potent reducing agents. Instead of just reacting with the solvent, they can be transferred directly to the substrate molecule you want to reduce.
And the most famous example is the Birch reduction.
Absolutely. The Birch reduction specifically reduces aromatic rings, like benzene rings. An electron adds to the ring, forming a radical anion. This quickly picks up a proton from a weak acid source present, like an alcohol added to the ammonia. Then a second electron adds, forming an anion which picks up a second proton. The net result is reduction of the aromatic ring to a non-conjugated 1-dendron-4-diene. It doesn't fully saturate the ring, it just breaks the aromaticity.
And where it reduces depends on the groups already on the ring.
Yes, there's regioselectivity again. Electron-withdrawing groups tend to end up attached to one of the remaining double bond carbons, while electron-donating groups tend to end up on one of the saturated carbons. It's all driven by the stability of the radical anion intermediate.
And didn't you say Birch reduction is used for alkynes too?
Yes, it's the standard way to reduce internal alkynes to transalkynes. The mechanism is similar: electron addition, protonation, second electron addition, second protonation. This nicely complements Lindlar's catalyst, which gives the cis alkenes, so you can choose which isomer you want.
Amazing toolkit for reductions. Okay, let's switch sides now and talk about oxidations. Again, control is key. We know some basics: oxidizing alkanes with ozone or OSO4, oxidizing alcohols with chromium reagents. But how do we get more selective, especially with alcohols? How do we reliably stop at the aldehyde from a primary alcohol or push it all the way to the carboxylic acid?
Right. That's the crux of it for alcohol oxidation. Secondary alcohols are pretty straightforward. Oxidizing them to ketones usually isn't too hard. Common reagents are chromium-based, like Jones reagent, chromic acid and acetone, or PCC, pyridinium chlorochromate.
But primary alcohols are the tricky ones.
They are, because the initial product, the aldehyde, can be oxidized further to a carboxylic acid, especially if water is present. Why? Because aldehydes can form hydrates in water, and these hydrates look somewhat like alcohols and get oxidized easily by strong oxidants like aqueous CRV.
Ah, the water's the problem.
Often, yes. So if you want to stop cleanly at the aldehyde, you need to use anhydrous conditions or specific reagents. PCC and dichloromethane is a classic choice. PDC, pyridinium dichromate, is another good one. These allow you to isolate the aldehyde without overoxidation.
What if the alcohol or the aldehyde product is really sensitive? Are there even milder options?
Definitely. For delicate situations, there are some excellent milder reagents. One is the Des-Martin periodinane, or DMP. It's an iodine V compound, works under neutral conditions, and is fantastic for oxidizing sensitive alcohols to aldehydes or ketones without causing side reactions like isomerization.
Okay.
Another very popular one is the Swern oxidation. This uses dimethyl sulfoxide, DMSO, activated by oxyl chloride, followed by a base. It's also very mild and effective, working at low temperatures. And there's TPAP, tetra and propylammonium peruthenate, which is a ruthenium-based catalyst used with a co-oxidant. Lots of options for mild selective aldehyde formation.
And if you do want the carboxylic acid from a primary alcohol or an aldehyde,
then you go back to the stronger, usually aqueous oxidants. Aqueous chromium, like Jones reagent, will do it. Or potassium permanganate, KMNO4, is another common choice. These will reliably take primary alcohols or aldehydes all the way to the carboxylic acid. Permanganate is even strong enough to oxidize methyl groups attached to benzene rings directly to carboxylic acids.
okay, so we have selective tools for both reduction and oxidation. Now, this leads to a really interesting idea: kinetic versus thermodynamic control in chemoselectivity. Sometimes maybe the reaction doesn't go to the product you expect based purely on speed.
Exactly. This is where things get subtle and fascinating. A great example is the acylation of an amino alcohol, a molecule with both an NH2 and an OH group. Let's say you react it with benzoyl chloride.
Okay, amine is more nucleophilic, so we expect the amide.
Under basic conditions, yes, you typically get the amide, which is usually the more stable product anyway. But here's the twist. If you do the reaction under acidic conditions, you often form the ester preferentially.
How does that happen?
Under acidic conditions, the amine group gets protonated, NH3+, making it non-nucleophilic. So the less reactive alcohol is the only group left to react, forming the ester. But it's more than just that. Sometimes these acyl groups can actually migrate between the nitrogen and oxygen. Under conditions where this migration is possible, reversible reaction, the system will eventually settle into the most thermodynamically stable state. Under basic conditions, the amide linkage is generally more stable. Under acidic conditions where the amine is protonated, the ester might actually be the more stable form overall. It shows that the product you isolate can depend not just on which reaction is faster, kinetic control, but which product is more stable under the reaction conditions, thermodynamic control.
Wow, so the conditions can totally flip the outcome based on stability, not just initial reactivity.
Right.
Okay, but what if you genuinely want the less reactive group to react first, and thermodynamic tricks don't help?
Yeah.
How do you force the issue?
Now we're getting into advanced strategies. One clever approach is react both, then selectively unreact one.
So how does that work?
Imagine you have two alcohol groups, maybe a primary, more reactive, less hindered, and a secondary, less reactive, more hindered. And your goal is to acetylate only the secondary alcohol. Trying to do that directly is hard because the primary one reacts faster.
Right.
So what you can do is just acetylate both groups first using excess reagent, get the diacetate. Then you use very carefully controlled mild basic conditions like potassium carbonate and methanol. Because the primary acetate is less sterically hindered, it will hydrolyze, deacetylate, much faster than the more hindered secondary acetate. So you selectively remove the acetyl group from the primary position, leaving the acetyl group on the secondary alcohol, which was your target.
That is sneaky. Using kinetics of the reverse reaction, essentially.
Yeah.
Very clever. What else?
Another neat trick involves dianions, or even trianions. There's a sort of rule of thumb. The anion that is formed last reacts first.
Okay. Explain that one.
Take one propanol. It has an alcohol OH and a terminal alkane CH. Both can be deprotonated by strong base. If you use two equivalents of base, you first deprotonate the more acidic OH, then the less acidic CH, forming a dianion. Now, if you add an electrophile, like an alkyl halide, where does it react? It reacts at the alkenyl anion, the one that was formed second last. It's often related to which anion is more reactive or perhaps less stabilized by ion pairing. It's a useful empirical observation that holds true in many cases, like in Volhart's synthesis of estrone, where a trianion reacts selectively at the last formed anionic center.
Fascinating. But these seem like quite specialized tricks. That's the most general go-to method for forcing reactions onto less reactive groups.
That would absolutely be protecting groups. This is the workhorse strategy.
The temporary disguise.
Exactly. Let's go back to that keto ester example. You want a Grignard reagent to attack the ester, but the ketone is more reactive. Simple solution? Protect the ketone first. A common way is to convert it into an acetyl by reacting it with ethylene glycol and an acid catalyst. Acetyls are stable to Grignards and strong bases.
So the ketone is now invisible to the Grignard.
Precisely. The Grignard sees only the ester, reacts with it as desired. Then, once that reaction's done, you just add aqueous acid. The acid removes the acetyl protecting group, hydrolyzes it, revealing the ketone again. You've achieved selective reaction at the less reactive site using the protect, react, deprotect sequence. It's incredibly powerful and widely used.
It really sounds like the cornerstone of complex synthesis. So let's talk more about this protecting group toolkit. What makes a good protecting group?
Okay, the key principles are: 1, it must be easy to put on selectively. 2, it must be stable, completely unreactive under the conditions you need for your main reaction. 3, crucially, it must be easy to remove cleanly and selectively under conditions that don't mess up the rest of your molecule. This last point is vital. We talk about orthogonal removal conditions.
Orthogonal meaning?
Meaning the conditions used to remove one protecting group won't affect other protecting groups or functional groups present. Each protecting group should have its own specific Achilles heel, a set of conditions that takes it off without touching others.
Makes sense. Can you give us a rundown of some common ones?
Sure. For aldehydes and ketones, as we said, acetyls, often dioxones made with ethylene glycol, are king. Put on with acid, stable to base nucleophiles, removed with acid. For alcohols, silly ethers are hugely popular, things like TBDMS, T-butyl dimethylsilyl. Put on using the silly chloride and a base. They're stable to many things, but their Achilles heel is fluoride ion, like TBAF, tetrabutylammonium fluoride, or sometimes acid. Different silly groups have different stabilities, giving you options. Another alcohol protector is THP, tetrahydropyranol. It's technically an acetyl. Put on using dihydropyran and acid. Stable to base, removed by acid. Benzyl ethers, OBN, are also common for alcohols. Very robust. Stable to acid, base, many reagents. Removed by catalytic hydrogenation, hydrogenolysis, that's their main Achilles heel. For carboxylic acids, T-butyl esters are useful, stable to base, unlike methyl or ethyl esters. Removed by strong acid, like TFA, trifluoroacetic acid, which cleaves the T-butyl group as a stable carbocation. For amines, we often use carbamates. The CBs, or Z group, benzoxycarbonyl is classic. Stable to many conditions, removed by hydrogenolysis, like benzyl ethers, or strong acid, like HBr. The Bach group, T-butyloxycarbonyl, is probably the most famous amine protector. Stable to base and nucleophiles, its Achilles heel is mild acid, like TFA, which removes it easily via T-butylcation formation and decarboxylation. And then there's FEFMOC, fluoromethyloxycarbonyl, another amine protector. It's stable to acid, but its Achilles heel is mild base, like piperidine, which causes an elimination reaction.
Wow, that's quite a list. Each with its own specific Way on, way off. The orthogonality is key, isn't it? Being able to take off one without touching another.
Absolutely essential for complex molecules where you might have multiple alcohols or amines that need protecting and deprotecting at different stages.
So bringing it all together, where
hmm
does this intricate dance of chemoselectivity and protecting groups really shine in the real world? What's a major application?
Peptide synthesis, without a doubt. Making proteins or peptides by linking amino acids together is arguably the ultimate chemoselectivity challenge.
Why is it so tough?
Well, think about it. Every amino acid, except proline, has a free carboxylic acid group, COOH, and a free amine group, NH2. Plus, many amino acids have other reactive functional groups in their side chains, alcohols, thiols, other amines, other carboxylic acids. If you just tried to mash two amino acids together hoping to form an amide bond, you'd get a complete mess.
Yeah, the amine of one could react with the acid of the same molecule, or they could link head to tail to head self-polymerize.
Exactly. You'd get unwanted side reactions like anhydride formation between two carboxylic acids, self-coupling, coupling at side chains. It would be chaos.
So how do chemists build peptides cleanly?
It relies entirely on the sophisticated use of orthogonal protecting groups. You have to protect the amine of one amino acid and the carboxylic acid of the other before you even think about coupling them. For instance, you might protect the amine with BOS, acid label, and the carboxylic acid as a methyl ester, base label, though often other acid label groups are used for the acid too.
Okay, so you protect N-terminus and C-terminus.
Right. Then you use a specific coupling reagent to form the desired amide bond between the unprotected acid of the first and the unprotected amine of the second. Then you selectively deprotect one end, say, remove the Bosco group with acid without touching the C-terminal protection. Now you have a dipeptide with a free amine ready to couple with the next N-protected C-protected amino acid. You repeat the cycle. Protect, couple, selectively deprotect, couple.
Building the chain one amino acid at a time, carefully controlling which ends react using those orthogonal protecting groups.
Precisely. Groups like BOC, FUMOC, CBZ, T-butyl esters, they are the absolute workhorses that make modern peptide synthesis possible, allowing chemists to assemble incredibly complex biological molecules like hormones, oxytocin, or neurotransmitters, gastrin. Fun fact, the artificial sweetener aspartame was actually discovered accidentally during research on gastrin synthesis.
That's incredible. It really shows how fundamental these principles are. We've gone from basic definitions of selectivity through the specifics of reductions and oxidations, managing tricky competitions, and finally to the art of protection and deprotection, enabling something as complex as peptide synthesis. It's clear that chemoselectivity isn't just about knowing reactions.
Not at all. It's about deeply understanding why reactions happen the way they do, the mechanisms, the electronics, the sterics. It's about knowing your reagents intimately. And when direct control isn't enough, it's about the strategic, clever use of protecting groups to guide the chemistry exactly where you want it to go. This kind of mechanistic thinking and strategic planning is what allows the synthesis of almost any molecule imaginable, and it forms the bedrock of retrosynthetic analysis planning, syntheses backwards.
A fantastic summary of Chapter 23 from Clayden, Greaves, and Warren. It really ties everything together. So as we wrap up this deep dive, here's a thought to leave you with. We live in an age of ever-increasing molecular complexity and information. What might be the next big Achilles heel chemists discover? Could AI help us find new, super-selective catalysts or reactions that allow transformations we can barely even dream of today? What new level of elegance and efficiency awaits?
Something to ponder. Thank you for joining us today as we explored this vital aspect of organic chemistry.
We really hope you found this useful and maybe even a bit inspiring. Thank you, as always, for being part of the Last Minute Lecture family.